Hi everyone, so here's the last video I'm going to do this evening anyway, Math 2010 question 3. Didn't mind this one actually, I thought this one was quite friendly. So you get this weird diagram here, but you know, we've got to prove a result in this first situation of x cos x is less than sine x is less than x. And they also tell us consider the various areas in the above diagram, and they've really drawn a triangle, a sector, and another right angle triangle. So I'm just going to basically take the areas of those in order. But what I'm going to do first, and this is just such a common trick, is I'm going to make the the hypotenuse of the right angle triangle 1, because that means I can just call this side cos x. Sorry, just suddenly looked at what I was doing. And this side sine x. In a similar way to, let's say you've got a force in mechanics and it's 15 newtons. This would be 15 sine whatever that angle is, and that would be 15 cos whatever that angle is. It's the same thing, isn't it? It's just SOHCAHTOA. If you call the hypotenuse of the right angle triangle 1, it makes your opposite sine x and your adjacent cos x, which is lovely because now I can just say, okay, so obviously, the OAC triangle is less than the OAC sector, which is less than the OAB triangle. That's what I'm going to point out. It should be obvious what I mean by that, I hope. You're probably thinking sometimes how you can explain yourself quickly without, writing too much stuff down because, time is precious in these kind of exams. Just try something which is like instantly recognizable for the examiner so they can see what you're doing. They just want to know what you're doing. Okay, so anyway, let's work these out. OAC triangle. Well, if I do half, now, OA to OC is a sector. And so that is also going to have a length of cos x, that OC bit. So we can use a half, we can basically use sine rule, a half AB, which would be cos squared x, sine C, which will be sine x. That must be less than, okay, OAC is a sector, that's a half r squared theta. So it's going to be a half cos squared again, but theta is x in this case, so we'll put a little x up there. And the right angled triangle is obviously a half sine x cos x. And you'll see straight away that from all three of these we can get rid of a cos and we can get rid of half. So we get cos x sine x is less than x cos x, which is less than sine x. Now straight away I was kind of happy because I thought, I think I've got the first bit, because look at that, it's just sitting there right there. So clearly x cos x is less than sine x. But also, let's just have a look at this first inequality that we've got here just a bit more carefully, because I did actually sit here and think for a second, like for at least 30 seconds, maybe 2 minutes and 30 seconds, what am I going to do next? How am I going to get the other one with x on its own? And then I just thought, what am I doing? Look, here it is. The cos x is cancelled, giving you x is bigger than sine x. See first two terms in inequality. Okay, so that means we can actually just state the result now. X cos x is less than sine x, which is less than x as required. Incidentally, looking at my notes from a few years ago, just after I sort of scribbled this one down, I thought I've just done that in the weirdest way earlier. I called it OA length 1, and I still managed to prove it, but when you're just like, why did I do that? It's, really silly move, really, in some ways. Anyway, part 2. Sketch y equals sine x over x. Now this is a classic. I've heard them ask questions like this in interviews before, for all sorts of unis, like because it's quite kind of an interesting question. But I've heard them ask for y equals x sine x before, and that's kind of like the reciprocal opposite, isn't it? And x sine x, incidentally, would get bigger and bigger and bigger and bigger and bigger as sine x increases, because of the the multiplier effect increases the peaks. And so this one, well, you're just dividing by x, and so it gets smaller and smaller and smaller and smaller and smaller. The one subtle bit which you've got, which they do flag to be fair, is justify your value of y that y takes as x becomes full. Now, I would like to point out very quickly that you've probably done small angle formulae by now, so you'll probably know that sine x is roughly equal to x if x is small. And the smaller x is, the closer sine x is to x, actually. I could easily justify it with a quick sketch. Basically, the gradient of sine x is 1 at the origin, and that's because sine x differentiates to cos x, and cos of 0 is 1. And y equals x obviously has a gradient of 1. And so if you just draw the diagram, you've got y equals x sort of coming in on top like that, and sine x going. And obviously, as you get further and further away, sine x is nothing like y equals x. But close to the origin, it's practically identical. So that's small angle formulae. And if you use that, you can easily see, so as x tends to 0, y tends to x over x, which is 1. So cool. We know it's actually going to start 1. It's going to do something like this. Just going to go down. It's going to have fewer peaks, basically. It's still going to have, though, all the other values, like sine of where sine x is 0. So not 0, but sine of like pi, for example. Yeah, it's definitely still going to hit pi. Sine of 2 pi. Yeah. It's definitely going to do that. Sine of 3 pi. It will have all of the same roots on the axis. Just not 0 because there's different behavior there, and that's the reason why you get that is because you might think, well, the top's still 0, but then you get 0 divided by 0, and that's not allowed. It's undefined. And as you can see, you're going to learn actually something called L'Hopital's rule. If you're doing further maths, you'll probably study L'Hopital's rule, and that gives you another way of finding behavior close to 0 there when you're dividing by 0. It's interesting stuff, definitely. Okay, so we've drawn that. Do they want anything else? Oh, you might want to point out that it's 1 here because it's tending towards 1. So that value is 1 if you like. You're going to get sine of 0, 0. Strictly speaking, it's undefined. Maybe you should say that there's a discontinuity at that point. It depends on what you're doing, but definitely it's tending towards 1. But yeah, anyway, okay. I don't think they were worried about the discontinuity. But part 3. We don't need to determine the coordinates at the turning points either. That's good. Okay, so drawn below is a graph of y equals sine x. Sketch on the same axis a line y equals cx, where c is bigger than 0. It's a positive gradient. And I wonder if this is going to... No, it never works on this thing. Okay, what I'll do is... No, I'm just going to have to draw it by hand. I'm going to have to draw it by hand. Oh, dear. Can I really not? Oh, yeah, here we go. Almost. Just down there, it's slightly inaccurate. You want it as a tangent, basically, at these points. And if you're as bad at drawing as I am, maybe just say next to it, tangent. Let them know that there's tangent there and there. Because then you've got 1, 2, 3, 4, 5, and so you've got exactly 5 solutions. And y equals cx hits the line y equals sine x. Okay, draw a line y equals c on the axes opposite. Now, straight away I thought, well, c is... If sine x equals cx, c is going to be equal to sine x over x. And this should have, apart from x equals 0 again, because of division by 0, but otherwise this should have the same roots as this equation here. In other words, that x-axis intercept is the same as this x-axis intercept, like they correspond on the other diagram. And also this one's going to be a repeated root, and this one's just going to be a standard root. So when I draw a line y equals c here, it should go through that line, and it should be actually tangential to the maximum on this graph. That's the line y equals c. Not sure I would have spotted that in test conditions. I could easily draw that just going through that and make a mistake there, but that's me. Okay, what we got next? Part 5. Yeah, are we already on part 5? Wow, just doesn't feel like we've done that much. Part 5, yeah. If x is the largest of the 5 solutions, okay, so this is x here, or even on this diagram, x here, yeah? Explain why tan x equals x. I think what they wanted you to do here, it's not what I did first time. First time I actually used quotient rule, but I think what they wanted you to do here, and this is what I did a few minutes ago when I did this question was just they said at the start, didn't they? Oh, you're allowed to use that sine x differentiates to cos x in this question. So I might as well, yeah. And on this sine x, I'm basically, yeah, I'm just going to make sure I've got the gradient function now of sine x, yeah. And so I'm just going to say, okay, my y equals cx has gradient, c. And so c equals cos x. Yeah, if it's a tangent there, c equals cos x. It's so much easier doing it that way because we know the gradient function of sine x, and therefore we know the gradient at every point on the curve. We can see c equals cos x. Oh, and I should make it clear that's cos of that capital X there as well. Yeah, because the gradient of sine x anywhere on the curve is just cos x, so I can just plug x in and find that c equals cos x because that's the gradient of the straight line. And so all I've got to do now to prove that tan x equals x is just observe that, well, we're solving here sine x equals cx, but c, I've just realized, is cos x. Now, that means sine of capital X equals capital X cos capital X, and the result just drops straight out. Tan x equals x. And that's that one. I really thought this was one of the shortest ones I've done really in a while, but yeah, hope you enjoyed the video. Hope it was useful anyway. Best of luck in the math.